Okay. Part 2, Maxwell-Cremona Correspondence. This one's going to be a little bit trickier. Not too bad, though. Let me just remind us where we are. Last time, we went from equilibrium stresses to reciprocal diagrams and back. So we showed that, if you have any of these, you can get one of these, and vice versa. Okay, so we saw it in both an existence sense, but also an algorithmic sense. We showed actually how to compute it. Now, this time we're going here. It's going to be very, very similar. The idea is we want to take a reciprocal diagram and get a lifting. I haven't said exactly what that is, but we'll do it in a second. Also, if you have a lifting of the graph, we want to get a reciprocal diagram, right? And then putting these together, we'll get this correspondence between these equilibrium stresses and liftings. All right, so here's the setup. Let G be planar and 3 connected. Let P be a drawing of G. When I say a lifting of G, what I mean is it's going to be a function from the vertices to the reals, or if you like, you can think of it as just a list of n real numbers, which says how high I'm going to lift every vertex. Okay, so I lift, here it is in the plane, I lift the vertex up by some height. And the rule is that the heights I lift, they need to satisfy the following condition, which is that if I have a bunch of points on a face, when I lift them up, that face has to kind of stay flat. Okay, so you should think of this as a point here in R3. Right, I had 2 coordinates for the point in the plane plus an extra coordinate, which is the height. So I've lifted this graph up into R3, and all of the faces had to stay flat. That's really the key idea. Faces stay flat. If I have a lifting, I can compute a reciprocal diagram. And here is one way to do it. For each face, right, there is some plane through the lifted points. And what I'll do is I'll just take fx to be the gradient of that plane. Hopefully you recall from basic calculus, right, the gradient of, if I think of the plane as a linear function, the gradient is going to be a vector in R2, right? It's the direction in which that plane is going up the steepest. It's really telling me which direction the plane has been slanted. I need to put the video here so you can see my hand waving, right? So if I slope up in this direction, my gradient is in this direction. All right, so if that's the gradient for the face, then if I look at an edge, and again, I'm using this notation, uv comma xy for the edge. So uv is an edge in the graph, and xy is its dual edge in the dual graph. If I do that, then it should be the case that if it really is lifting the faces flat, then the change in the height at these 2 vertices u and v, it should just be the gradient times the vector, right? The dot product of the gradient with a vector tells you how much you changed height in that direction, along that length. So in this case, what we get is the gradient of the plane for x times this vector pu minus pv, it should be equal to the change in height, right? So the lifting gave me this height, and it guaranteed me that these gradients really were going to describe the changes in height, and it would be the same thing at y, right? Because I only have one height function, so it doesn't really matter which side of the edge I look at it from, I'm still going to get the same change in height. And since these two are equal, if I subtract this from both sides to move it over and regroup, what I get is fx minus fy times pu minus pv is 0. But that just means that these are orthogonal. And if they're orthogonal, then the use of the gradients as the coordinates for the dual faces turns out to be exactly what you need to get a reciprocal diagram. All right, so from a lifting to a reciprocal diagram, really, really easy. From a reciprocal diagram, we can also get a lifting. So in other words, we have this reciprocal diagram F, and you can think of it, or we would like to think of it as a gradient. That is, for every face, it's going to tell us how that face is sloped. And we want this h, which is really a kind of height function. And going from a gradient to the function that has that gradient, well, that's something you know something about. Hopefully, that's a kind of integration. And so really what we're doing in this step is a kind of discrete calculus. Right? So as soon as we take f and treat it like a gradient and try to find this function, we're really doing a kind of simple discrete integration. All right, so if we have f, we know that for every edge, right, there's some change in height, and we know what that change of height is supposed to be now. We don't actually know what h is, but we know what the change in h is because we have f, we have p. Okay, so this is the edge uv is incident to x. I could have put y here as well, and it would still be true. All right, so we want to solve for these changes in height, or actually we want to solve for the height given the changes in height. So if I wrote this, this equation out for every edge, well, the left-hand side, that's just the co-boundary times h, right? Because it'll give me for every edge the difference of this function along that edge. In the right-hand side, we're just calling this b. So it looks like, again, just a linear system to solve. I know the right-hand side, and I just want to solve for h. So we're in a similar situation to previously where we have a linear system, we know what it is, we just want to solve it, and we want to know, can I solve it? Like, is there a solution to this linear system? And again, that means we're looking to see, like, is b in the image of that co-boundary map? But this, of course, is also equal to the kernel of the boundary of h. And so we can just try multiplying the boundary of h times b and see if we get 0. And if we do, then we know that this system has a solution h. So let's try that. So if I do dh times b, this is going to be a vector with, what is it? It has an entry for every face. So let's pick out some particular face x. So this boundary is going to sum up over all the neighbors of x in h of whatever b is, right? So this be value. So this is like summing over all these edges. Again, I'll call them uv, xy, and this x is the same as the x here. So it's all the edges where there's some y adjacent to x, and this is uv is the dual edge. Then we know that that is just fx times pu minus pv. Right, that's what I got right from here. And if I look at this expression, you see that this term fx doesn't depend on the edge, so we could actually pull that out. And then the sum here, this is actually just equal to fx times the boundary of h times boundary g transpose p. Okay, because what did I do? I'm taking sums, summing over all the edges of the differences, right? And so that's just dh, and this is dg, this is co-boundary of g times p is like gives me all these differences. Okay, so if you just multiply them all out, that's what you get here. And this, again, is 0. Okay, so that confirms that, in fact, b really is in the kernel of dh, which means it really is in the image of the co-boundary map here. And so there really is a solution. Okay, so that's our important final step here, is that we really do have a solution to this linear system. So we can just solve, again, in this case, it's a boundary system, to find h, and that'll give us the height function. It'll tell us exactly how to lift it up. And And again, it all kind of hinges on carefully aligning the orientations of our boundary and co-boundary maps. Now, that maybe isn't the most satisfying way to, I think, get a feel for what's really happening. If you were to do this maybe more algorithmically, you might try the following idea, which is that if someone told you the gradients, and the gradients are, there's only a finite number of them, there's one for every face, you can see, the first thing is that I shouldn't expect a unique solution because, well, if I take whatever height function I have and I just lift it up by more, I don't change any of the gradients, but I would get a new height function. So I know that I have some freedom, and I might as well just pick one vertex, let's say v0, and set it to be height 0. And now if I know what the gradients are, I could kind of walk around the graph and fill in the heights on all the other vertices on that face. At least this first face, if I know what its gradient is and I know one point, that's enough. Incidentally, this adding a constant value is exactly the plus c you always saw when you did integration in high school. All right. So if I could do this, I could just kind of assign one, and I could walk around and just assign all the other heights on the face based on the gradient. And now I know the new gradient over here, and I've already figured out the heights for two of those vertices, and so I can kind of keep going. And you can imagine just walking through the graph, filling in the heights as you go. And in any given face, it turns out everything is good. And what I mean by that is if you sum around a face, the sum of the changes in heights, well, those changes in heights are going to be this kind of telescoping sum. See, it gives you a nice cycle where P0 minus P1, P1 minus P2, P2 minus P3, P3 minus P0, and all these terms cancel out. Okay, so around any cycle, you know you're going to be consistent. But the thing you have to worry about is that any larger cycle, you're still going to be consistent. Now, this should also look maybe familiar to from a multivariable calculus class, right? If you have a gradient, you would like to know if there's an antiderivative, and so you would like to ask questions about things like conservative vector fields, right? Like if I take some path, does it matter which path I took? And in this case, that's like saying, does it matter which order I visited the vertices to assign heights, or will I get different answers from different paths? So if there was some path that gave me a cycle, when I come all the way around again, it tries to give me a different height for v0. Well, here's the neat trick, is that I use the fact that the faces are good, and if the faces are good, I can add the solution on the face, because it comes out to 0. I can turn it into a shortcut here. That is, I can kind of push this over the face and get a new cycle, which would still be a contradiction. But I can do it again. So if I continue to do this, you'll notice that I just keep getting down until I get down to just one face, and we know that everything is good on a face. That is, the sum of the changes in heights around a face are always going to be is always going to be 0. All right, because the gradient there is always fx. So so you may have seen this same kind of argument in a multivariable calculus class, except not done in this discrete way, right? Where it may be argued that some kind of closed curve could be contracted to a point. And here we're doing that contraction one face at a time. And so same thing happens, and this is kind of like the pictorial algorithmic view for why if you solve this linear system, you really will get a solution. Because the first way you would go out and solve it is you would just walk along the edges of a spanning tree. There's no need to go around a cycle. And if you only cared about the edges on a spanning tree, that's only n minus 1 equations that you'd have to satisfy, and you have n variables. Right, so you can solve that. So what we actually saw when we wrote out all this was really just rewriting any cycles in a basis, right? It actually naturally falls into the basis of faces. And since the faces of a planar graph form a basis for the cycle space, it naturally allowed us to kind of reduce the question about any cycles to just the questions on faces. All right, so let's wrap up here. So this gave us the second half of the Maxwell-Cremona correspondence, going from spring constants and equilibrium stresses to nice dual drawings, which are orthogonal, right? Every edge is orthogonal to its dual drawing, and liftings, keeping faces flat. Okay, and this will give us a way to connect some of these algebraic ideas about graphs to some more geometric ideas, in particular thinking about geometric ideas not just in the plane but lifted up into 3D. Okay, so stay tuned for that.